Hi guys, welcome to Chem 223. My name is Dr. Mortensen. Okay. First off, let's talk about me and my family. This is a picture of me and my family in front of our house. This obviously is me up in top, my beautiful wife Lisa, and our three kids, Violet, Chloe, and Peter. And then last year we decided, you know what, let's go for one more. And we had little baby Cynthia, and she's adorable, and she smiles. She's got really chubby hips, and it's really cute. And then, of course, we've got our two puppies, Belle and Luna. And this is our family. Everyone has aged a little bit since these pictures were taken. This was taken when Belle and Luna were, I think, 8 or 9 months old. They're now a year and a half, so they're a little bit bigger. Cynthia here is now about 6 months old. Beyond my family, I enjoy writing science fiction and fantasy novels for fun. Both of these two are on Amazon right now, selling like hotcakes. And by that I mean I've gotten a few of my family members to download them. Now in Chem 223, I like to start the class off by introducing a motto. And the class motto is, "Put on the name of Jesus Christ." So hopefully, through me sharing my testimony throughout this semester, you'll be able to develop a stronger relationship with Christ, and hopefully you'll take some responsibility on yourself to develop that relationship as well. The learning objectives for this class are: 1, to gain an understanding of statistical data analysis. That'll be your favorite part of the class, I'm sure. The second part is to learn current best practices in analytical chemistry. And 3, become better at critically analyzing scientific results. The structure of the class will be as follows. I'll be posting lectures every Monday and Wednesday in video format just like this. I'll be putting them on the schedule page on Learning Suite and also in the content section. There will be reading associated with each lecture, and then a quiz indicating whether or not you did the reading and watched the lectures. So these quizzes will account for about 25% of your grade. Let's jump over to Learning Suite. I will show you where to find all this stuff. Okay, now you should be seeing Learning Suite. I have Chem 223 open right here. Most of the coursework I'm going to try and post on the schedule page. You'll notice that yesterday all of these lecture and reading quizzes for the class opened up, so don't be freaked out that there's a billion assignments on that page. That's just the open date for these quizzes. The way this is set up is that all your lecture material and reading should be in this far left column. So you'll see for today you need to read chapters 1 and 2. I've already posted the PowerPoints for the lectures for lecture 1 and 2. And then once I'm done recording this video, I'll be posting a link to the video here. And I'll generally email out lectures to you when they become available as well. I will be recording lectures Monday and Wednesday and posting them after I record them. So don't necessarily get too worried if they're not posted at midnight or something like that. Then every Friday, your reading quizzes will be due. These are due at midnight on Friday. I'll just show you what they look like. Each exam basically looks like this. Did you watch lecture 1? Yes, some of it, or no. I'll let you decide what you feel is the best answer for these questions, whether it's yes or some of it or no. Yes will receive 1 point, no will receive 0 points, and some of it will receive half points. So we're relying on the honor system here, especially since we're at BYU. I tend to trust my students quite a bit. I haven't had too many problems with this. And then the second question is, did you read chapter 1? That's the reading associated with this lecture. And again, you just answer yes, some of it, or no. Okay, let's go back to the schedule now. So that is on the left. The next thing that you'll need to take care of is your homework. So the homework is done through Sapling Learning, and there is a link here for registering for that. let's jump back over to the PowerPoint and I'll talk a little bit about how that is going to work. Okay, for homework, that's all going to be done through Sapling. Like I said, that's online. You need to register for it. All of your assignments are going to be due Friday at 11:55 p.m. I'm kind of a mean professor in that I make everything due on Friday instead of Saturday and force you to have a weekend. For the homework, you'll have an unlimited number of tries for each assignment until the due date. Now, when people first hear this, they get excited. This is the way I run all of my classes generally. I give students unlimited tries without penalty. And students get excited because they think, oh great, I'm gonna get all sorts of points, and that's true, you will. The downside though is it seems to take students much longer than to finish their homework assignments than regular. I think the reason for that is because people just keep trying different numbers to see if they're right without giving much thought to the changes they've made. With this class, most of your answers on your homework are going to be numerical, so I'm not too worried about you just trying every answer. Occasionally that'll be an option, but for this assignment, or for most of your assignments, it won't be, since they'll be numerical answers. And don't keep trying forever on these assignments. If you spend more than an hour on a single problem, that's a good sign that you need to stop right there and ask for help. I've enabled you to have discussions with each other through Learning Suite. I am also generally fairly approachable. If you need help, feel free to reach out to me by email anytime, and we can set up a Zoom meeting to work through your problems. Now, you can do your homework late. Each day that you do late comes with a 10% penalty for anything you haven't finished. And you have until the last day of class to finish all of your assignments. On the last day of class, that means the day before reading day, all of your Sapling assignments become unavailable. Your homework is weighted as 30% of your final grade, so I strongly encourage you to get all of it done. Let me show you really quick what your homework should look like. So if you pull up Sapling, it should look like this. You'll notice there's due dates and upcoming assignments here. You'll notice there's actually 4 assignments due this weekend. One is a practice assignment that just gets you familiar with Sapling and gives over some review things. And then there's a chemical equations training. These are both counted for points, though you should be able to get all of it done fairly easily. But you'll especially want to do the chemical equations training because doing chemical equations and so forth in Sapling can be kind of tricky, and so that teaches you how to do it. And then we have an assignment due, or assignment associated with chapters 1 and 2 due this weekend as well. Now, normally in this class we have labs. And these labs are obviously not available to us this semester. And so what we're going to be doing is I will be recording videos of myself or my TAs doing different lab work associated with the labs, and then I will be providing you with mock data that you will analyze and submit through Learning Suite. So let's jump back really fast to Learning Suite. On Learning Suite, over here, you'll notice in this third column on the schedule, I have lab material. We're not doing anything in the lab this week. Next week, you will have Lab 0, which is spreadsheet training. This is a spreadsheet that gives you instructions on how to fill out spreadsheets and how to use them. Should be fairly self-explanatory. If you need help, let me know. And you'll be turning that in through Learning Suite, through this spreadsheet training button. You'll just go to the submit button, and it doesn't give me an option to submit, but it will give you an option to upload your completed spreadsheet training through there. Other labs, you will be downloading the lab procedures and will be required to be familiar with those procedures. And then you will have a spreadsheet posted here. It's not posted yet because I haven't developed all of the mock data, but the spreadsheet will be posted here along with the videos from the lab, and you'll be required to watch the lab video and read the lab procedures for each lab. And then your lab report will be due on Friday for each week. So for example, in weeks where we have 2 labs, like in week 4, both labs will be due Friday. And they will be due as a quiz. I'll grade that quiz on the various factors, including significant figures, which we will go over next week. If you have any questions about any of that, feel free to let me know. So, like I said, lab reports will be due Friday by 11:59 p.m. You'll be submitting those online, either uploading a file or completing a quiz. Your labs will be weighted as 30% of your final grade. Your labs will be weighted as 30% of your final grade, and you have to complete all of the labs to pass the class. Finally, we'll have a final exam. This is our only exam of the semester. It'll be administered through Learning Suite. It'll be weighted as 15% of your final grade. It'll cover the entire class. You'll have a 3-hour time limit for it. It will be open book, and you will be able to use Excel on that exam. And throughout this class, you're going to have to learn how to use Excel fairly well. And so that spreadsheet training that opens up next week will be great benefit for you. And if you have questions on how to use Excel, feel free to reach out to me or other students in the class. For office hours, usually I hold regularly scheduled office hours, but with the given format of having an online class, I don't think that's very practical. And so all office hours will be by appointment only. You'll need to reach out to me by email, and I will set up a Zoom meeting for us. I'm a fairly approachable guy. I'm pretty nice, so don't be afraid to reach out to me. Okay, that covers the structure of the class. Now we're going to go over a couple of topics that you'll need to know for the class. The first one is serial dilutions. It also includes a little bit of washing glassware. I start with a flask, and it has 1 liter of a 2 molar sodium chloride solution. So this is pretty salty. The Great Salt Lake actually only has a salt solution. The Great Salt Lake actually only has a concentration of about 0.46 molar sodium chloride. So this is way saltier than Salt Lake. Let's say now we dump this solution out and there's just some drops left at the bottom. Let's say there's only about 1 ml remaining at the bottom for convenience. And then we do 1 rinse of this guy with 500 mils of water, and we dump that all out. Now there's just 1 liter down here remaining. What's the concentration of that? Well, it's 0.004 molar. You can still taste that. So here we dumped out this salt solution, we rinsed it 1 time with water, and now this remaining stuff down here has a concentration that is still salty enough to taste. So let's try this again, but instead of rinsing with 1 douse of 500 mils, let's rinse it 3 times with 100 mils each time. So again, we're starting with this 2 molar sodium chloride solution. We've dumped it out. There's 1 milliliter left down at the bottom. Then we rinse with 100 mils of pure water. Well, after that first rinse, we've now dropped the concentration down by a factor of 100. So now it's 0.02 molar. We rinse it again with 100 mils of water. We've dropped that down now to 0.002 molar. And this is now below your taste limits, or below most people's taste limits. And if we rinse it a 3rd time, drop that concentration of this 1 milliliter droplet down here by another factor of 100, Now we're at 0.000002 molar. So if we compare this value to the value that we got when we rinsed one time with 500 mils, you'll notice that now we're 20,000 times more dilute than we were, even though in this case, we only used a total of 300 mils of water to rinse this guy out, whereas before we used 500 mils to rinse it out. So the takeaway here is that you can get down, or you can get your concentration down much more quickly by doing serial dilutions with small volumes than you can by doing a single dilution with one volume. A practical application of this too in the lab is that it's better to rinse a bunch of times with small amounts of water than to just fill your glassware with a bunch of water one time. And of course, you're not going to be rinsing glassware, but I generally make a point to my students to not leave DI water running into your glassware to get it clean. And this is for two reasons. One is that it wastes a lot of DI water, and we have to pay for that. It's not an astronomical cost that we're not willing to pay for using for normal glass or for normal lab use. But the second reason is because as the water comes in here and fills this guy up, your water actually just hits here and spills right out the top and doesn't mix down in here. So even if you're leaving your water running into your glassware, you're not really changing the concentration at the bottom of your glassware very much. And so just rinsing for a long period of time with running water doesn't usually do you very much. Okay, so I've kind of introduced serial dilutions. And to figure out these new concentrations, I had to use an equation. This equation right here, C1V1 equals C2V2. Now this is an equation you should have seen previously in Chem 105 or 106, but all this means is that the concentration times volume of your starting solution is equal to your concentration times volume of your ending solution. And this, of course, is an equation we use when we're diluting solutions or when we're concentrating them sometimes too. So right now, I have a beaker full of analyte solution. The concentration of my analyte is 25 millimolar. I have a graduated cylinder that goes up to 100 mils, and I have unlimited plastic pipettes and unlimited DI water. What I want to do is to make a 100 mil solution that has a concentration of 10 millimolar of my aqueous analyte. So the question is, how much analyte solution do I need to add, and how much water do I need to add? Go ahead and pause the video right now and see if you can't work this out by yourself. And then once we come back from being paused, I'll work through the solution. So go ahead and pause. Okay, here's how you should do this problem. So we have C1V1 equals C2V2, and we can plug in values that were given in the question into that equation. Our starting concentration is 25 millimolar. So we put that in for our C1. What is our V1? Well, we actually don't know V1. That's what we're trying to solve for. You might think it's the volume in your beaker, but it's not. It's the volume you take from here and add to your graduated cylinder. That's what we're trying to solve. We know that our final concentration, we want it to be 10 millimolar. And we know our final volume, we want to be 100 milliliters. So then we just rearrange this equation and solve for V1. That just looks like this. We plug those numbers into our calculator, and we get a value of 40 mils for our analyte solution. The next question was, how much water do we need to add? And for this one, we don't have to do a lot of fancy math. We know that we're trying to make a 100 mil solution. We know that we added 40 mils of our analyte, so that last 60 mils has to come from water. So that's just subtraction. Okay, so this is a straightforward problem, but in analytical chemistry, we actually don't use graduated cylinders very much. We actually tend to use glassware that looks like this. What I'm showing here is a 10 mil volumetric pipette. So this is calibrated very precisely to where this red line right here, I don't know how well you can see that in the video, but there's a red line right here. And if you fill up to there, then you get exactly 10 mils of solution. Over here, what I'm showing is 200 ml volumetric flasks. So these are similar to the pipettes, except these, of course, you don't suck solution up into, you put the solution into it. And these also have little graduated lines right here, right here. And if you fill up to that line, then you have 100 milliliters of solution. We often also use plastic pipettes, but we don't measure anything with them. We can use those to add water to these volumetric flasks until we get up to that 100 ml line. Okay, here's another practice problem for you though. With this glassware, how do we go from a 25 millimolar analyte solution to a 0.5 millimolar analyte solution? Go ahead and pause the video right now and see if you can't figure out a method for doing this. Here's how we would do it. We would first take our 10 ml volumetric pipette. We would take 2 aliquots of our analyte solution and put them over here into our volumetric flask. We would then take water using these pipettes over here and fill our volumetric flask up to the 100 ml mark right there. This will give us a final volume in this container of 100 mils and a final concentration of 5 millimolar. Right, so we've gone from 25 millimolar now to 5 millimolar. Let me know if you have questions about that. The next step that we would do is from this solution that has 5 millimolar in it, we would take one more aliquot of that and put it in this other volumetric flask, which is behind my words over here. And then we would fill the rest of this guy up with water. So we moved 10 mils of 5 millimolar over here. We diluted it with water up to the 100 mil mark, which is right about here. So now our final volume is 100 mils, and our final concentration is 0.5 millimolar, which is exactly what we want. Let me know if you have any questions about that. You might remember this equation right here for K, where K, our equilibrium constant, is equal to the concentration of our products raised to the power of whatever coefficient is in front of them in the equation, divided by the concentration of our reactants raised to the power of the coefficient in front of them. Some rules for equilibrium constants. All of our solutes are listed in moles per liter, so that's anything dissolved in a solution. Any gases are recorded in bars, and pure solids, pure liquids, and solvents are omitted from the equation. So we don't include, for example, water in this equation. Or if one of our reactants or products is a solid, we wouldn't include that in there either. Okay, so let's practice with this a little bit. I have this equation right here where zinc is reacting with ammonium to give us zinc 2 plus hydrogen gas and ammonia. So let's write the equilibrium constant for this reaction. We get this, where K is equal to the concentration of the zinc 2 plus ions times the pressure of the hydrogen gas in bar times the concentration of ammonia raised to the second power, because ammonia has a 2 coefficient in front of it there. And then on the bottom, you'll notice we didn't put zinc down here. Why? Why did we not include zinc as a reactant in this equation? The answer is because zinc is a solid, and solids don't go into equilibrium constants. So we just have the ammonium ion concentration on the bottom here raised to the second power because of this 2 coefficient in the equation. Now with equilibrium constants, let's review our acid-base dissociation constants. So if you'll remember, an acid generally has this equation when put in water. So you have your acid with a proton that reacts with water and gives up a proton and gives us this H3O plus complex, or you can also write this just as H plus a negatively charged conjugate base. So our equilibrium constant for this reaction looks like this. Ka is equal to the concentration of our conjugate base times the concentration of H3O plus divided by the concentration of our acid. Or it can also be written like this. This equation right here is the exact same as this, except that H3O plus has been changed to H plus. The reason we sometimes write this as H plus and sometimes as H3O plus, because it's generally believed that this free proton forms a complex with water and sticks to it, but functionally these two equations are identical. And then for bases, we have our base equation in water. So base, as you'll remember, steals a proton from water. And so our base will react with water to form BH plus OH minus. So then our base dissociation constant, Kb, is just equal to Hb plus times OH minus concentration divided by the concentration of our base. If you have any questions about that, let me know. And of course, these are both used for weak acids and bases, which we'll review later in the semester too. Then the last equilibrium constant we need to talk about today is Kw. So Kw, of course, is the auto dissociation constant of water that describes how much H plus and OH minus are in water. And we can derive this actually from the equations for acids and bases. Let me show you how we do that to start with. So if we start with the equation for an acid and the equation for a base, and we line these up, now you'll notice, of course, I changed my notation here for the base to be A instead of B. So this is A minus, so we're actually using the conjugate base of our acid up here. But if we combine these two equations and add them together, then some of the things cancel out. So HA is going to cancel out on either side. A minus is going to cancel out on either side. And we're going to be left over with water on the left for both reactions. So if we add those together, we get two waters. We'll still have our H3O plus and our OH minus. And this is the equation then that describes the autoionization of water. So what does Kw actually look like from these? Well, since we're adding these two equations together, we actually have to multiply their K values together. So Kw then is equal to Ka times Kb. Ka, of course, is equal to A minus concentration times H plus concentration over HA. Kb is equal to HA concentration times OH minus concentration over A minus. Of course, HA here will cancel out, the A minuses will cancel out, and we're just left with H plus and OH minus. Now, you don't necessarily have to remember this whole derivation or this one up here. It's important that you understand where it comes from, but you don't necessarily need to memorize the derivation. But you do absolutely need to know this relationship, that Kw is equal to Ka times Kb. And that's going to be very important throughout the semester. Now let's review some other factors associated with K values. So let's say I have two reactions. I have this reaction up here where A plus B is going to C plus D, and this one where W plus X is going to Y plus Z. The K value for reaction 1 is 26,000, and the K value for reaction 2 is 12. The question I pose to you then is, which reaction reaches equilibrium more quickly, reaction 1 or reaction 2? Think about that for a moment. You can pause the video if you want. The answer, of course, here is we don't have enough information. Just knowing the equilibrium constant doesn't give us any idea of how quickly it reaches that equilibrium constant. It could take days or months or years or seconds or microseconds or nanoseconds. That time scale doesn't actually affect these K values. It's not reflected in them at all. Another factor we need to review is a value similar to K, known as Q. So the equation for Q looks identical to the equation for K, but functionally these two equations are different. The way that they are different is K describes our reaction at equilibrium, Q describes it before it's at equilibrium. So K here is a constant, Q varies depending on what time you're looking at in your reaction. So if you just first throw A and B together, you're going to have 0 C and D in there, and so your Q value will be 0. If you wait forever until this reaches If you wait forever until this reaches equilibrium, then Q is going to be equal to K. Okay? But if your Q value is greater than K, which direction will this reaction move in? So let's think about this. Q is greater than K. To increase the value for Q, we have to increase the amount of products, decrease the amount of reactants. Of course, if this has more products than it would at equilibrium, then those products are then going to react to give us more reactants. And so it's going to shift this reaction to the left. If you have questions about that, feel free to reach out to me. This, of course, gets us into Le Chatelier's principle. If you remember, what Le Chatelier's principle says is if you add some to the left, you'll shift the reaction to the right. If you add some to the right, you'll shift the reaction to the left. But it gets a little trickier than that in practice, and let me give you some questions to help you identify why that gets a little more tricky. If we add equal moles of B and C to this reaction, which way will the reaction shift? Well, there's 3 moles on the C here, and there's 1 on the B here. So does that mean we have to add 3 times as many C to cancel out the number of B? Or does that mean that 1 mole of C is 3 times more than B? Well, actually, the question doesn't even require us to think that way. The reason is because B here is a solid. Because B is a solid, it's actually not going to factor into our equilibrium constant. And Le Chatelier's principle is actually only associated with affecting the equilibrium of our reaction. So we change Q, and then Q tries to get back to K. So if you add equal moles of B and C, this is going to shift to the left because B is a solid, doesn't show up in our equilibrium constant, but C is an aqueous species, does show up there. So if you add more to the left here, we're going to shift, or sorry, if we add more to the right here, we're going to shift the reaction to the left. Next question. If the size of the reaction vessel is doubled, in which direction will the reaction shift? Okay, for this question, we have to think, what does doubling the reaction vessel size do? I didn't say we're doubling the quantity of products or reactants present. We're keeping those exactly the same. So you can think if this reaction here is happening inside a plunger or inside a syringe, and we pull the plunger of the syringe back, which way do we shift the reaction? Well, is changing the volume going to change what a solid is doing? No. Is it going to change what aqueous species are doing? No, it's not. They're still going to be inside their liquid, and the liquid has a fixed volume. The thing that doesn't have a fixed volume is a gas. So as we pull back on that plunger, we're going to increase the volume of course, our gas is going to have some sort of equilibrium partial pressure that it's going to try and achieve. So if we increase the volume here, we're going to shift this to the right because we're going to want to produce more gas to balance that out. The last things we're going to cover today are SI units. You should remember what most of these are. You might not remember the values of them, but you should review these tables. These are found in your book in chapter 1, I believe. And you should remember that length and mass and time are measured in specific units. You should be able to recognize all of these SI units. So we're not going to go over them in detail in the lecture because I think that you can mostly just review them in the book and that'll be sufficient. You should also be familiar with the prefixes we add to SI units, such as kilo, centa, milli, micro, etc. I've highlighted here the ones that we use most often. You don't necessarily have to remember iota and zeta and so forth, but you should be able to understand where to look those up if you need them. And again, we won't be reviewing these on the lecture today, but you should make sure to refamiliarize yourself with any of them if you've forgotten them. You'll also need to remember how to do unit conversion, and you'll need to be familiar with these other common units that are derived from base SI units here. So I have their base psi units listed here. I have their values listed in other psi units here. And of course, their symbols. So things you need to know are things like frequency, force, pressure, etc. And again, these are things that I think you can review on your own. So that does it for lecture 1. Feel free to reach out to me with any questions, especially if you're having trouble finding out how to register for Sapling.